Hi, my name is Frederick Simons, and I work at Princeton University. And I will talk to you about EarthScope-Oceans, closing the oceanic coverage gap for seismology and environmental sensing. My collaborators listed here are all working at different institutions, but we're all united in the academic consortium of EarthScope-Oceans, which we started about 5 years ago. First of all, everyone knows IRIS and the Seismological Society of America, of course. This is a map of the 46 and some thousand instruments that have at one time collected data that are now available for request from the IRIS data management centers, all mostly on land. This here is a map of the oceanic coverage of the Argo program, which is measuring conductivity, temperature, and depth on 10-day cycles, profiling the first 2 kilometers of the world's oceans. Now, 50 years ago, Hugh Bradner started conquering the oceans for seismology. This is an instrument that he put together that had a 3-axis geophone that was floating mid-water for the very first time and collected data mostly to characterize the oceanic noise environment. It was not good enough to record earthquakes, but it was good enough to record the power spectral density of the noise in the oceans, which affects almost everything that we observe on land. Here's an example of a sonobuoy with a hydrophone, an instrument not unlike the one that Bradner put together a few years later in 1973. And you're seeing somewhat clear arrivals of P waves, S waves, and then the hydroacoustic phase T that were recorded by these types of freely floating instruments. Very noisy. Some 50 years ago, John Orcutt, Jeff Babcock, Guus Nolet at Princeton University and the Scripps Institution of Oceanography took one of the Argo-type solo floats and equipped it with a hydrophone and sent it on its way to try and record with great precision actual earthquake conversions, earthquakes that come from the other end of the world and convert at the ocean bottom into hydroacoustic phases. This is Martin Rappa from the Scripps Institution of Oceanography deploying one of these freely floating Mermaid instruments. And Mermaid 001 here stands for Mobile Earthquake Recording in Oceanic Areas by Independent Divers. What did we record? A few earthquakes. One of them in particular here at the top is a teleseismic earthquake of a magnitude 6 and at a distance about 50 degrees, 5,000 kilometers away, that clearly shows that a teleseismic arrival, a mantle phase, could be recorded by a freely floating instrument. On the left is a pressure record filtered between 0 and 1 hertz, and on the right is a time frequency spectrogram, where you see that the little bit of energy that is coming in around P here, zeroed at P, the arrival time of the compressional wave conversion, is right in the middle of this noisy band, but nevertheless clearly shows up. For contrast, I'm showing a smaller earthquake, a magnitude 2.7, at a distance of about 100 kilometers, that shows you all of its energy that hasn't been sapped yet by attenuation in the Earth, and that therefore shows up as a quite clear arrival across all of these frequencies. Now, teleseismic earthquakes is what we want to record with Mermaid, and so the top line is the types of phases that we're most interested in, to do global tomography, to properly time the arrival of these compressional waves and integrate them into tomographic models of wave speed variations in the Earth's mantle. Some 10 years ago, we reached the second phase of Mermaid, a larger instrument made by TW Web Research in Falmouth, Massachusetts, and we sent it on its merry ways across a variety of oceans, to begin with the Mediterranean, but also in the Indian Ocean and the Pacific. On the left, we see a variety of teleseismic phases, P, bouncy phases, PP, core waves, PKP, that have been recorded over the years by this instrument. And on the right, we see pressure records of a swarm of earthquakes that have been recorded in the Indian Ocean that had otherwise not at all been recorded by any other instrument. Mostly smaller earthquakes, mostly not of use for global tomography, but yet very clearly visible. 5 years ago, Jan Hello at the GeoAzur in France developed a grounds-up redesign of Mermaid, which is now our 3rd generation. And the design drawing is here. It's a large sphere filled with lithium batteries, but again, it has a hydrophone, an Iridium GPS combined antenna, so we can keep time and we can locate the instrument when it is at the surface. It can relay the data in near real time via Iridium, and it can also receive messages by which we can interact with the instrument to request data and to update mission parameters. What you're seeing at the bottom here is a connector for additional sensors, which is how we aim to extend the usability of this type of mobile mid-water column device so that we can plug in additional sensors for all sorts of other types of observations. So 3 years ago, we started a campaign whereby ultimately 50 instruments were deployed in French Polynesia. These instruments are light, they're easily deployed, one throws them overboard, and a day later, we're getting the first earthquakes on our servers. The instruments are not meant to be recovered, they're completely autonomous, they listen for the acoustic wave field, they report what they think is teleseismic earthquakes, and then they go back and complete their mission. These instruments here, they live for 5 years. So these are coming to an ocean near you. Right now, we have 47 active instruments recording and reporting earthquakes on a daily basis. On average, one mermaid completes a dive and resurfacing cycle every about 6 days. So like Argo, they complete repeated dives and surfacing cycles, and like Argo, they come back around on a weekly basis. Here are some examples of teleseismic earthquakes recorded by Earthquake, a record section of 2 different earthquakes on the left in the Fiji Islands, on the right in the Kuril Islands. Again, both of them picked up by a variety of mermaids drifting around in the Pacific. So we're seeing quite clear arrivals, and we're meaningfully extending the oceanic coverage using this new instrument. And of course, the details of the arrivals are lost in the axis here, but so we are able to time with very great precision the arrival of these particular teleseismic phases so that we can use them for seismic tomography. The scale here is between 5 and 50 degrees along the surface of the Earth and between 60 and 95, so we're capturing a whole suite of epicentral distances for every global earthquake. Here are some details of the arrivals showing or illustrating how we analyze the data in post-processing. We very precisely try to measure the arrival time and its uncertainty, and we're capturing the details of the waveform. The grays are the noise, the blues are when the signal has started, which we have timed. And so we are building a large database of arrival time residuals compared to reference models that again we can put into global tomographic models. Now Mermaid records much more than just the first arriving waveforms. An earthquake will generate surface waves, it will generate direct waves of the P and the S, the compressional and the shear wave variety, and it would also generate hydroacoustic phases which mostly propagate into the oceanic water column and travel over great distances. We have been measuring core phases, an example of which is here, PK, IKP interacting with the Earth's core, PKP as well. And here is a long time series of records. Now, Mermaid in its normal operation modes really just sends us about 200 seconds of that little waveform that contains a primary arrival, which is of most use for us to do mantle tomography. But of course, there is much more on these records. This is an example of what we can get when we talk to the instrument and ask it to give us a long time series. And it is also an example, a rare example of a recovered mermaid when we happened to be close during one of the deployments and we captured one that had been floating for a whole year so that we were able to read out its 1 year buffer. What you're seeing here is arriving is the P wave conversion, is the S wave conversion, is a whole suite of modes developing, and then finally traveling at the water speed at much higher frequencies is the hydroacoustic T phase. This central band, of course, is the large noise that is omnipresent in these records and that we will be studying in more detail. So removing all the earthquakes, removing all the transients, removing all the ships, all the little blips of transient energies that are not generated by the ocean, we are left with these power spectra of the infrasonic ambient noise. Here, 2 months, a population of noise spectral densities. The central red line is the median, and the white lines are the 5 and 95 percentiles. And comparing the graphs on the left and the right, we are seeing variations in infrasonic ambient noise as recorded by our instrument, which floats at 1,500 meters depth in the oceans. What are these variations then do? What are the power variations at different frequencies do? Well, they are driven by the wind and wave generated ocean surface gravity waves. If we isolate that frequency range here in red, we are seeing a spectral shape of the pressure variations recorded by Mermaid. And now in black, we're comparing that with an ocean model. This is for one particular week of the Mermaid, of that particular Mermaid. And we're seeing the shape here of the surface-driven pressure variations matched by the shape of what Mermaid records at depth at double the frequency. So here is the double frequency mechanism of the secondary microseismic sources at work. If we filter in the area where there is most coherence here, we are seeing in red Mermaid's pressure, and in blue this wave watch model of ocean state being very, very coherent. Weekly variations are summarized here with every point. And so we're seeing that what Mermaid records at depth is primarily in this noise band generated by the surface ocean. Here's a full map of the coherence between what Mermaid records as pressure variations at depth on the y-axis, and on the x-axis, the ocean model that predicts what the ocean surface gravity waves are doing. The dashed line is the doubling frequency line, and the red areas are those areas of very, very high coherence. So Mermaid, between about 0.8 and about 0.08 and about 0.8 hertz, is recording primarily the driving, the ocean state, in other words. So in addition to earthquakes, this really truly is an environmental sensor because it is measuring something of the oceans. Noise from the surface is recorded, and then the earthquakes are recorded from depth. Our consortium is called EarthScope-Oceans, and we have plans to double the amount of instruments in our array. We have 50 now, we're aiming for 100. And so we're inviting the community to contribute instruments, to also potentially give us requests so that we can talk to our instruments and bring back to you records of phases or waves or intervals of time of interest. And that is the goal of our consortium EarthScope-Oceans. Here's some references of the papers that we have published on this. Thank you very much.